Just think about the solar system. How big is it? Now think about the atomic structure or atom. How small is it? But the bigger system of the universe and the smaller system of the universe, nicely they are in the same pattern. And not only that, in a standard size of the water droplet, there are approximately 5 into 10 to the power 21 number of atoms present. So just think about how small an atom is. Myself, Tanmoy Datto, Assistant Professor, Department of Chemistry, JS College of Engineering, welcome you all in my 4th lecture of atomic structure. We already discussed about the Rutherford's model, Bohr's model, Sommerfeld model, Zeeman effect, Stark effect, and also de Broglie theory. In the previous class, we discussed about the Zeeman effect and Stark effect, which are very much related with the splitting of the spectral lines in presence of either magnetic field or electric field. Then we discussed about the wave-particle dual nature according to the de Broglie theory. And also we discussed about the differences between electromagnetic wave and the matter wave. And today we'll discuss about the 3 principles. That 3 principles are very much important for electronic configuration. Pauli Exclusion Principle, Hund's rule, Aufbau principle. Heisenberg uncertainty principle, its application, or we can solve few numerical problems, and then we will discuss about the Schrödinger wave equation and a brief concept of the wave function. So students, without further delay, let's come to my class. Ground state electronic configuration depends upon the 3 principles. First one, Pauli Exclusion Principle. Second one, Hund's rule, and the third one, Aufbau principle. So today we will discuss one by one principle, and depending on the concept of that 3 principles, actually we do the electronic configuration. That means how we can put one electron in a particular orbital of corresponding subcell. That theory, that concept came from the 3 principles: Pauli, Hund, and Aufbau principle. So first one is the Pauli Exclusion Principle. So Pauli Exclusion Principle totally depends upon the quantum numbers. Already we discussed in the previous class that there are 4 quantum numbers: that principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. And that 4 quantum numbers came from the 4 model or the 4 principle or the 4 effects, like that Bohr's model, Sommerfeld model, Zeeman effect, and the Stark effect. So now today, if we consider any electron, any particular electron like 2s1. So if 2s1, then we can write down in that way. So if it is the first electron, then how we can write down n equals to, it will be corresponding to that value. This is the principal quantum number. So n equals to 2. Then n is the principal quantum number. Azimuthal quantum number will be 0, because here S subcell is denoted. That means if S subcell is denoted, that means obviously here L equal to 0. If L equal to 0, magnetic quantum number M equal to obviously 0. Then the remaining part is the S. S means spin quantum number. So for example, we are taking the first one, this is the plus half. Now if we take the 4 quantum numbers for the remaining electron, like if we consider that the next electron will be it, and for that case n equal to, it will be again 2, it will be again 2, and n equal to 2, again L equal to 0, as the same subcell is here, that is the S. m equal to again 0, because if L equal to 0, m equal to obviously 0, and s equal to minus half. That means for the first one, it is the for first case, that is the set of the quantum numbers, and it is the second set of quantum numbers. Now look here, for the first case, like 2 and 2, principal quantum numbers are same for the both cases. Azimuthal quantum numbers are also same, and magnetic quantum number is also same, but the spin quantum number, that values are not same. So think about here that if we consider that 2 electrons for any particular subcell or any orbital, then what happens, that the probability that maximum 3 quantum numbers can be same but not the fourth one, and this is actually the Pauli Exclusion Principle. So what is the Pauli Exclusion Principle? How we can write down the statement of the Pauli Exclusion Principle, students? You can write down the statement of the Pauli Exclusion Principle in that way, that the 4 quantum numbers for any 2 electrons of an particular atom never be same. There is a probability that maximum 3 quantum numbers can be same but not the fourth one. So students, you have to keep in mind the statements, because that statement is very important for your exam purpose. So you have to write down the statement, and you can give the any of the example like that there are maximum 3 quantum numbers may be same but not the fourth one. And depending on that principle, also we can predict in that way, if it is the particular orbital, the spin quantum number varies in that way. So obviously their maximum probability of carrying the electrons will be 2, because if one spin it is the plus half, another spin it will be the minus half. So what happened actually, the maximum carrying capacity of the electrons in a particular orbital there will be 2. From that information also we can get from the Pauli Exclusion Principle. One orbital cannot carry beyond the 2 electrons. Okay, so this is the Pauli Exclusion Principle, and that concept is very important for the ground state electronic configuration. Okay, so now we'll move to the next concept, and that is the Hund's rule. Hund's rule is very much helpful to determine that how electrons will be filled up in the orbitals under same subcell. That means if the orbitals are within a particular subcell, then obviously its energy will be equal. If its energy will be equal, then the Hund's rule helps us that how we can put one by one electron of all the orbitals of that particular subcell. And according to Hund's rule, the pairing of the electrons in the orbitals under same subcell only possible when all the orbitals of that subcell will be singly occupied with parallel spin. That means if we consider that the electronic configuration is that 2p4, okay, if the electronic configuration is 2p4, then we can write down, or we can put the electrons according to Hund's rule, that it is the 2p is the subcell, and there are 3 orbitals, px, py and pz. Okay, we already discussed in the previous class. So now if the px, py, pz are the orbitals, then what happened? According to Hund's rule, the electrons will be filled up, or electrons will pair when all the orbitals of the subcell singly occupied with the same spin, then it will be paired up. That means more specifically that electronic configuration, that means 2p4, we can't write down in that way. This is also 4, but we can't write down in that way. So this is the right configuration. but this is not the right configuration. This is the Hund's rule. What is the maximum multiplicity? I will explain later, and from there also it will be more clear that why that kind of configuration is right, but the next one is not the right. Okay, I'll give you another example, like it is the 3D6. Okay, so now I will show you that what will be the electronic configuration of 3D6. So it looks like, so there are for the D, you know, for D subshell there are 5 d orbitals are there. So if there are 5 d orbitals, then obviously I can give you the electrons like that, 1 2 3 4 5. So according to Hund's rule, all the orbitals will be singly filled up, so the electrons are singly filled up. Okay, then it will be paired up. So then it will be paired up. So this is the right configuration. But if we write down that configuration, that 3D6 in that way, so if I put the electrons in that way, 1 2 3 4 5 6, that is not the right configuration. So you have to keep in mind that Hund's rule is very, very important for the electronic configuration. When you are putting the electrons in the orbitals of a particular, that what is very, very important, that for a particular subshell. So for a particular subshell, when you are giving the electrons one by one orbital, already you know from the previous concept that one orbital can carry maximum 2 electrons, but you can't put the 2 electrons at a time for that particular orbital. You have to put one electrons on all the orbitals of that particular subshell. Then you have to come back to the first one for the pairing of the electrons. Okay. So now come to the next topic, that maximum multiplicity. So you know that I think you can see that kind of terms, that Hund's rule of maximum multiplicity. So generally we called it Hund's rule, but there are two words are also associated with the Hund's rule. So that the words are the maximum multiplicity. So you should know that what is the meaning of that maximum multiplicity. So maximum multiplicity means, here maximum multiplicity indicates that maximum spin multiplicity. Maximum multiplicity means it is the maximum spin multiplicity. So maximum spin multiplicity equals to 2s plus 1. Okay, 2s plus 1. Now look here, it is called the maximum spin multiplicity. So that means where we will get the maximum value, maximum spin multiplicity. So it is actually spin multiplicity. Okay, so spin multiplicity equals to 2s plus 1. So now where we will get the maximum value, that will be maximum spin multiplicity. I can give you the example for that case. Okay, so for general case, like if it is the 2p2, okay, for any example 2p2. So if we draw 2p2 like this, 1 1. Okay, so now for the first case, look like here I can put the values of s. What is the s? S is the total spin quantum number values. Like in this case, both the cases, it will be here s equals to plus half. That means 1. Okay, so plus up, that means it is the parallel spin. Okay, not opposite direction spin, so the value will be same. Okay, so that will be the plus up, so plus up, so the value will be same. So s equal to 1, so 2 into 1 plus 1, that equals to 3. Okay, now you can also put the two. It is the right method. I will show you. If it is wrong, then what will be the value of the spin multiplicity. for 2p2 you can also write down the values like that, or you can put the electrons like that. It is not right, but I'll show you that how the spin multiplicity value affect here. Okay, so now if you calculate the spin multiplicity value, then what happened? It will be 2s plus 1 in the same way. So now what is the value of s? Here s equal to, for 1 it is the plus half, and another one obviously it is the minus half. So for first one it is the plus half, and for second one it is the minus half. So that means it will be the 0. So if it is the 0, what will be the 2s plus 1 value? So 2 into 0 plus 1, that means 1. Isn't it? So that means finally what we are getting, the spin multiplicity value for the first case, here it is the 3, but the next case it is the 1. So now think that which will be the right configuration, either this one or this one. Okay, so according to Hund's rule, you know it is the maximum spin multiplicity. So maximum spin multiplicity means where we are getting the maximum value. So look here, in the first case it is the maximum value, so obviously it is the right configuration, but that one is not the right configuration. So this is the wrong configuration, because here for the same electronic configuration, here we are getting the one value spin multiplicity, so it is a lower value, but we'll always will move to the higher spin multiplicity. So that means it is the right one, and we have to always follow that method of spin multiplicity. So you have to keep in mind the Hund's rule also, statement also, and you have to show the examples that how Hund's rule can be applied during the electronic configuration. And another question is very important, that why Hund's rule is called the maximum multiplicity, or what is the meaning of the maximum spin multiplicity. Then you have to show that kind of example. Okay, now we will discuss about the Aufbau principle. Okay, so first of all I will tell you something, that like the previous two principles, Hund's rule and the Pauli Exclusion Principle, maximum students think that Aufbau also it is the name of the scientist, because maximum of the principles are according to the name of the scientists. So it is the general concept of the students that Aufbau was also a scientist, and who discovered or who gave the first time that principle. That's why it is called Aufbau principle. But your concept is not right. Actually, Aufbau is a German word. Okay, so what is the meaning of Aufbau? So Aufbau means to build one by one. To build one by one. So Aufbau means to build one by one. Okay, so when we will discuss the Aufbau principle, then we will understand that why this is called Aufbau principle. That means that something regarding the building of one by one. Okay, so now the question arises, that I think one question is in your mind. So who first gave the principle? Actually the scientist is very much famous to you, and already we discussed in our previous class about the name, or we discussed about the principle or the theory of that scientist, and he was the Niels Bohr. Okay, so actually first Niels Bohr placed the theory, but it is known as the Aufbau principle. Now why it is known or it is called the Aufbau principle, you will understand when we will discuss the theory. Theory tells about that. Already you know that in one orbital contain maximum 2 electrons. Pauli Exclusion Principle also told the same fact, and Hund's rule also told that how the orbitals will be filled up for a particular subcell. So now the question arises that how subcell will be filled up one by one. That means in p orbital, we know from the Hund's rule that px, py, pz, how it will be filled up, we already know from the, we understand from the Hund's rule. And also in Pauli Exclusion Principle told that in px there will be maximum 2 electrons in opposite spin. So now question arises that how 1s, 2s, 2p, 3s, how one by one that subcell will be filled up. So obviously that concept or that theory depends on the Aufbau principle. So I think all of you understand very well that what is the Aufbau principle. Aufbau principle told that how one by one subcell will be filled by the electrons. That means there must be some sequence by which we can put the electrons one by one subcell, isn't it? So Aufbau principle told that fact, and there is a theory also that electrons will be filled up according to the increasing energy order of the subcell. Okay, so according to Aufbau principle that we can put the electrons in one by one subcell according to the increasing order of the subcell. Now how we can understand, or I think it also in your mind, that how we can understand that which subcell has the higher energy than the other. So for that purpose also Aufbau principle gave one equation or one formula by which we can understand which subcell has the higher energy, and the rule is that where n plus L value will be higher, that subcell will be higher energy. Okay, so that means we have to check the n plus L value, that means the summation of the principal quantum number and the azimuthal quantum number. Then only we can understand or we can compare that what are the energy order of the subcell, one by one subcell. I can give you one example. Okay, the common example that in between 1s and 2s, how you can understand that which subcell has the higher energy. For that purpose what you can do, here you have to calculate n plus L value. So n value is 1 and L value 0. Already you know that for S subcell L value is the 0. So n plus L, 1 plus 0 equals to 1. And second case, here n plus L value, that means 2 plus 0, that means here 2. Okay, so second case, here principal quantum number 2, n plus L value means here principal quantum number value 2, that's why 2, and azimuthal quantum number value 0, so that's why 0. Here principal quantum number 1 and azimuthal quantum number 0, so that's why 1 plus 0 equals to 1. So that means, look here, the 1s has the lower energy than the 2s, because here n plus L value lower with respect to 2s. So obviously when you will give the electron, then you have to follow that order. That means first there will be 1s, then 2s. Okay, so first here there will be 1s orbital or subcell, then it will be 2s. So when you have to put the electrons here, at first the 1s will be filled up like 1s2, then it will be 2s2. Okay, so in that way we can continue the electronic configuration. I can give you another example where you can predict the electronic configuration, or the how you can put the electrons from one by one subcell from the n plus L value. For example, if you take the example of the 2p and here is the 3p. Okay, 2p and 3p. Or I can give you another example. There it will be the 1s. Okay, so just calculate each and every case what will be the value of the n plus L. So according to n plus L value, it will be 1 plus 0, it will be 2 plus 1, it will be 3 plus 1. So it will be 1, it will be 3, it will be 4. Okay. So if it is 1, 3, 4, then the energy order will be like that. So 3p will have the higher than 2p and 1s. Okay. Then I can give you another example. I can give you another example. There 3D and 4s. This is the most common example. I think all of you know. There is some exception. That's why we have to keep in mind that example always. So if it is 3D, 3 plus 2, that means it is the 5. 3 plus 2 means it is the 5. And 4s means 4 plus 0. That means it is the 4. So expected that, what is the expected? So it looks like that the order will be like that, 4s will have the higher energy than 3D. But actually what happened at first, 4s will be filled up to, then electron comes here. Okay, so you have to keep in mind that when you are giving the electrons, like if I put the order 1s, 2s, 2p, 3s, 3p, then at first 4s, then 3d. So here the fact you have to keep in mind that electrons will come at first the 4s, then it will go to the 3d. Okay, that is very, very important point. And from here also look that here 5 has the higher energy than 4, so that means 3d has the higher energy than the 4s. So obviously that's why at first electron will come to the 4s, then it will go to the 3d. Then I will give you some another example of where you can't predict the order from the n plus L value. Okay. Okay, so students, just do it and try it, that either it is possible to determine that from L plus L value we can predict that in which subcell electron will go first, or is it possible to write down the order, increasing order of the energy of the 2p and 3s or not. Okay, I can show you that here if you calculate the n plus L value, it will be 2 plus 1, that equals to 3, and here if you calculate 3 plus 0, that equals to 3. The most interesting case is that for the both cases here n plus L values are same. So then n plus L values are same. Okay, then at that moment what you have to do, you have to concentrate. So keep in mind, when n plus L values are same, then only we apply that theory, the next theory. Otherwise you can't apply the theory. Okay, so when n plus L value same, we have to concentrate only n values. Okay, so where n value higher, that subcell has the higher energy. Okay, is it clear? Where n value is higher, when n plus L values are same for the two subcells, then only we can apply the theory. And what is the theory? The theory is that we have to concentrate only the n values. Where n value higher, obviously that subcell has the higher energy, and in that way we can tell that, or we can conclude that at first electron will go to the 2p, then 3s, as the 3s has the higher energy than the 2p subcell. Okay, there is another way by which we can also determine the order of the, or the energy order of the subcell. Okay, one theory is that we can easily calculate by n plus L value. Another theory is that we can also predict that order from the rainfall method. Okay, now what is the rainfall method? A rainfall method is that, okay, just look at the board. So I just here the one by one subsets are there. Okay, then what happened? Rainfall method. So it looks like rain. So think about that. It is raining. Okay, so it is heavily raining and it is a rainy day. Okay, so I think so many images are in your mind when I am telling about the rainy day. Okay, that first of all, I think you think about that it is the holiday. Okay, so it is at that moment it is not the holiday. So look at the board. Okay, so if we consider that, so we have to follow the order, the arrow. Okay, so arrow means you have to follow the arrow means here first we have to consider the 1s. So here we can write down 1s, then just come here, then 2s. So then we can write down 2s, then again come to the 2p. So again 2p, then after 2p it comes to 3s. So write down 3s. Okay, then I start here from here. Then after 3s it will be 3p. So it will be 3p. Then after 3p it will be 4s. Then after 4s it will do 3d and so on. Okay, so look here that what we determined previously from the n plus L rule, that 3d has the higher energy with respect to 4s, also reflected here, that 4s will be filtered at first, then 3d, and this is the rainfall method. You have to follow the arrow, then again backside, then again front side. Okay, in that way if you place the subcell, then you can get the sequence of the subsets by which you can put one by one electron in the particular subcell. Okay, so this is the all about your Aufbau principle, and in that Aufbau principle, or in this Aufbau principle, what you can determine that the how one by one subcell are coming according to the energy order, and how you can put the electrons in one by one subcell. Okay, so this is the complete concept of the electronic configuration: Pauli Exclusion Principle, Hund's rule, and Aufbau principle. And keep in mind that without the three principles, it is not possible to do the electronic configuration or downstate electronic configuration. So you have to keep in mind that three principles are the three pillars of the ground state electronic configuration. Now we'll move to the Heisenberg uncertainty principle. You know, for large system or macroscopic system, we can determine the position and the momentum exactly at a time by the Newtonian mechanics. But what happens in case of microscopic body? Or very small system like electron, the associated wave character does not allow the application of Newtonian mechanics. So according to Heisenberg principle, Heisenberg uncertainty principle, it is totally impossible to determine exactly the position and the momentum or maybe velocity of an electron simultaneously. That means if we want to determine the position more accurately, then there will be big error in the momentum. That means the uncertainty or the error. Or if we want to determine the momentum more accurately, then there will be big error in the position. So the two parameters, either position or momentum or position or velocity, the two parameters we can't determine exactly at a time. Okay, so that's why according to Heisenberg uncertainty principle, if delta x, that means del x, it is the uncertainty, that means error. If the delta x is the uncertainty in measuring the position of an electron, and delta p, it is the uncertainty in measuring the momentum at a time, then what happened according to uncertainty principle, Heisenberg uncertainty principle, it greater than equal to h by 4 pi. What is the value of Planck constant? Planck constant equals to, it is the, what is the value? 6.624 into 10 to the power minus 34 joule second. So it is the value of Planck constant. Some kinds of numerical problems also you can see in the question paper, that by applying that equation at that time we have to use the equation delta x into delta p, that equals to h by 4 pi. So that will be the Heisenberg uncertainty principle, or you have to use that equation at that time, but generally we have to use the del x into delta p greater than equal to h by 4 pi. Now there is another case, that velocity. So how we can establish the relationship regarding the velocity? So we can write down here delta x into delta p, that means we can write down m delta v, you know that p means the momentum, so momentum equals to mv, so here uncertainty will be delta v, so m into delta v, that greater than equal to h by 4 pi, or we can write down delta x into delta v, that greater than equal to h by 4 pi m. So if there is any relationship regarding the delta v, then you have to use that equation also. So this is the mathematical expression for the Heisenberg uncertainty principle, and we have to use that Heisenberg uncertainty principle in the mathematics also, or numerical problems also. Okay, so let's check one numerical problem from the Heisenberg uncertainty principle. Okay, so now we'll solve one problem from the Heisenberg uncertainty principle, and this is the numerical problem, and what you see here, that calculate the uncertainty in velocity meter per second of a moving object of mass 25 gram if the uncertainty in its position be 10 to the power minus 5 meter, then you have to calculate the uncertainty in velocity, and the Planck constant that is given here, that h equal to 6.626 into 10 to the power minus 34 joule second. So you have to solve the problem from the equation del x into del p equal to h by 4 pi. So you have to solve the problem from the equation of the Heisenberg uncertainty principle, del x into del p, del x into del p, del x into del p equal to h by 4 pi from that equation. So students, what you can do, you can just take a screenshot and try to solve, pause the video, try to solve the problem, then when I will solve the problem, just you have to check with your answer and procedure either it is right or wrong. So you can just take a screenshot. Okay, so now this is the solution of the problem. So I am explaining that how you can solve the problem. So first of all, what I told you, the problem depends on the Heisenberg uncertainty principle. So according to Heisenberg uncertainty principle, we can take del x into del p equal to h by 4 pi, and as you know that del x is the uncertainty in the calculation or determining the position, and del p is the uncertainty in the determination of the momentum. So now here in the question, what is the given? Here given that is the mass equal to 25 gram. So here we just convert it in the gram to kg. Okay, that all the units are in SI, that meter here or joule, whatever. So here it is given in joule second. So we are taking the unit m, mass equal to kg. Okay. So now look here, that is the given, and another thing, that is the 10 to the power minus 5 meter. What is it? It is the uncertainty in its position. Uncertainty in its position means it is the actually del x. Okay, delta x. So uncertainty in measuring the position, delta x. So when we are taking the delta v here, so here will be delta x will be here, and that is a 10 to the power minus 5, and m, that will be also here 0.025. So just put here the values of each and every term, like starting from h is the Planck constant 6.626 into 10 to the minus 34, and then 4 is here, pi 3.14, 10 to the minus 5 for del x, and 0.025 for m. The answer will be 2.099 into 10 to the minus 28 meter per second. So student, I think all of you have done or able to solve the problem in your copy also. What I told you each and every class, that when you attend my class, please take a copy and pen. You have to make a note also. When I am discussing something, you have to write down in your copy, and when I will give you the problems, then you have to solve the problem at first, then you have to pause the video, you have to solve the problem, then you have to check with me that either check with my solution that either it is right or wrong. So I hope that your solution is also right and you also determine the right answer of that problem. Motion of the various macroscopic objects can be explained by the classical mechanics, that means Newton's law of motion, but the motion of the various microscopic objects cannot be explained by the classical theory. Why? Because classical theory ignores the two facts. First one, classical theory ignores the wave nature of the particle. And the second thing, classical theory also ignores the uncertainty principle. So that's why classical theory is totally unable to explain the motion of the microscopic particle, whereas quantum mechanics came to the field. And you know, there are two famous scientists who were working at a time but independently and established the quantum mechanics. It was the year of 1933. The Heisenberg and the Schrödinger both independently established the quantum mechanics at a time. And you know, in 1933, Schrödinger won the Nobel Prize for his famous Schrödinger wave equation. So what is the Schrödinger wave equation? Schrödinger wave equation is that del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus 8 pi square m by h square into e minus v equal to 0. Now what is the psi? Psi is the amplitude of the electron wave. What is the x, y, z? X, y, z are the coordinates. M is the mass of the electrons, and all of you know very well what is the h. H is the Planck constant, and v is the potential energy, and E is the total energy. Now psi, actually it is the electron density around the nucleus, like a wave. Okay, so this is called the wave function, and we generally we take it as the atomic orbital. Now there is some condition or to be satisfactory values for the psi. That means it may be acceptable. So what are the conditions? Conditions will be psi must be continuous function, it should be finite, and it should be single valued. And the probability of finding the electrons around the nucleus should be unity. Actually, in the syllabus of BTech first year chemistry course of module 1 atomic structure, the syllabus is very much limited up to that point, and that's why I will not go to a detailed discussion about the wave function or Schrödinger equation or like that. So students, you have to keep in mind in the basic concept of the psi, what is the psi and the Schrödinger equation. Now students, come to the point, what are the shape of the S orbital, P orbital, that is Py, Px, Pz, and the D orbitals, that means a dxy, dzx, dyz, dx square y square, and dz square. Shape of the S orbital. So it is almost spherically symmetrical. What is the spherically symmetrical? That means it remains in the x, y, and z direction. It remains in the x, y, and z direction in the same way. That's why it is called the spherically symmetrical shape of the S orbital. Now if you consider the p subshell, then in the p subshell there are three orbitals are there. So first one px, second one py, and the third one pz. So what is the differences, or what are the differences between px, py, and pz? If you consider, or if you look carefully, the px orbital, it is along the x axis. If you look carefully, the py orbital, it is along the y axis. And if you consider the pz orbital, it is along the z axis. And looks the orbitals, that p orbitals looks like a dumbbell shape. Dumbbell shape means it almost the electron density is the two direction, up portion and the down portion, and the middle portion, that is called actually node. That means their almost electron density is 0. So what is the shape of the p orbitals? That looks like dumbbell shaped. Now come to the orbitals of the d subshell. Then there are 5 orbitals. You already know that there are 5 L values of the for the d subshell. So that's why there are 5 d orbitals are there. First one dxy, second one dyz, third one dzx, and then dx square y square and dz square. Now there are some differences between the first 3 and the remaining 2. The first 3, that dxy, dyz and dzx, that 3 orbitals are in between the axis. But if you consider the last 2, dx square y square and the dz square, they are on the axis. That means if you consider dxy, they are in between x and y axis. If you consider dyz, they are in between y and z axis. But if you consider dx square y square, they are, or it is actually on the x and y axis. Like same case for dz square. And also just take a snapshot for the questions of today's class. And today there is some MCQs are also available for the overall chapter of the atomic structure, because this is the last chapter of the atomic structure according to your syllabus. So you have to solve the MCQs also, and you have to solve the questions also. You have to write down the answer of that questions also. And see you in my next class, which will be the first lecture of the periodic table. Goodbye. Take care.